Hello, in this video we are going to talk about side chain reactions of benzene. That means reactions at the benzylic positions. Okay, so we will talk about reactions at the benzylic position. And what would be benzylic position? The carbon atom next to the benzene ring. Okay? So if you have a alkyl group like this, then this carbon atom will be the benzylic position. Okay. You can have benzylic position this side too. So for example, if you have an alkyl group here, that would be a benzylic position again. Okay, this green carbon atom. Let's write it down. What type of reactions are we going to look at here? First one is oxidation. Okay. So if you take a benzene ring and try to oxidize it, and for that we will need oxidizing agents. Some of the strong oxidizing agents are like sodium dichromate. Usually we do it in an acidic medium, 3O+. Actually, when we do this reaction with benzene, we don't have any reaction. We do not see any reaction. On the other hand, if you have a alkylated benzene, like for example, if you have a methyl group here, and then you do the oxidation with the same oxidizing agent, sodium dichromate, acidic medium, we get benzoic acid. So this carbon atom with 3 hydrogens is converted to a carboxylic acid like this. Okay. All alkyl benzenes can be converted to benzoic acid as long as there are hydrogens at the benzylic position. Okay. So what I mean by that is, say for example, you had a benzene with a ethyl group, then also when you oxidize it, Na2Cr2O7 H3O+, you will again get benzoic acid. Okay, this is what the major product is. There are some side products which I'm not writing right now. So the condition is that you should have hydrogens at the benzylic position. Okay, so see, this is my benzylic position and you have hydrogen atoms. When would be a case when we do not have hydrogen atoms there? When benzene is substituted with a T-butyl group, right? See here, this is my benzylic position again, this carbon atom here, but we do not have any hydrogens there. So when this molecule is treated with oxidizing agent in presence of an acid again, there is no reaction. Okay, so the necessary condition for oxidation of alkylated benzenes should be that we should have a hydrogen atom at the benzylic position. This oxidation can also be performed with other oxidizing agents like KMnO4. Okay, so sometimes you will see Na2Cr2O7 as your oxidizing agent, and sometimes you will see KMnO4, and both are good oxidizing agents. Okay. This is also a good oxidizing agent, powerful one. Okay. Let's look at the second reaction at the benzylic position, and that is the bromination. Okay, so when we take benzene, and it's a free radical bromination. Okay, so for that we will need, say for example, I have again a methyl group here, because we are doing reactions at the benzylic position, not at the benzene anymore. Okay, so in the previous video we saw reactions where benzene was getting substituted by different functional groups. However, in this case, in our present video, we are going to talk about reactions, particularly focusing on this benzylic position. Okay. All right. So in this case, if you treat the alkylated benzene with NBS, okay, if you recall from organic chemistry 1, NBS is N-bromosuccinamide. It is a source of bromine radicals, and if you treat that in the presence of light, which we represented by H nu, you can substitute the hydrogen at the benzylic position, okay, with a Br. Okay. So we had 3 hydrogen atoms here at the benzylic position. Now we are we have substituted one of the hydrogens with a Br. So this is also a very useful reaction because we know that alkyl halides can be converted into many other functional groups, which are extremely important. Okay. For example, you can do a nucleophilic substitution reaction where if you treat this molecule with sodium hydroxide, right? If you treat it with sodium hydroxide, it's a primary alkyl halide. So you can substitute the Br with the OH, okay, like an SN2 type of reaction. So for having an alkyl halide at the benzylic position can be extremely useful. So keep this reaction in mind while when we are doing synthesis. This may be very handy reactions. Okay, and a third reaction that we would do, it's not really a benzylic position reaction, but a reduction reaction. Okay, that means normally when you take benzene and treat it with hydrogen in presence of palladium over carbon, we do not see any reaction. Okay, these are the normal reducing conditions when we studied the reduction of alkenes and alkynes. However, we can make the benzene or reduce the benzene. For that, we need a much harsher condition, and that would be at a very high pressure and very high temperature. So if you take benzene and treat it with hydrogen over nickel, okay, nickel is a metal, with 100 atmosphere pressure, okay, so pretty high pressure, and at a high temperature like 150 degrees Celsius, these conditions will make us help the benzene to reduce, sorry, this is not the correct structure. We can reduce the benzene to a cyclohexane. Okay, so that means we have removed all the pi bond, and for this we need a lot of harsh conditions, severely harsh conditions like high pressure and high temperature. So these are the 3 reactions that we are using in electrophilic aromatic synthesis reactions. Okay? All right. So let's now look at a few examples of synthesis. Okay, that means taking benzene as our starting material and converting it into different substituted benzene. Okay. So let's begin with one here, so the question will be, let's write down the question, that starting with benzene, how will you synthesize the following compounds? How will you synthesize the following compounds? And the first compound we are going to look at is we have aniline here. I mean the brominated aniline. So benzene is still in the molecule with NH2 here, NH2, and then bromine is D. Okay? So if you want to write down the overall reaction of what the question is asking, so you have to take benzene and then convert it into this target compound where we have two functional groups, NH2 and Br. Okay. So how do we do this type of reactions? Do we know any reaction where we can place an NH2 group on benzene? So we have not studied a direct method of forming aniline from benzene, right? Aniline is this benzene with the NH2 group. However, we know how to convert benzene to nitrobenzene and then reduce it to NH2. Okay, so maybe it will be a good idea for us to keep a summary of the benzene reactions here drawn. Okay, so I'm going to just draw a summary of benzene reactions which we have studied earlier. So here is benzene. Then if I want to convert benzene to nitrobenzene, which is NO2 here, then the conditions are I should take concentrated HNO3 and concentrated H2, so both strong acids. Okay. Now, if I want to convert benzene to a halogenated benzene like X, then I have to treat it with X2 halogen and in presence of AlX3. Okay, that means the Lewis acid. Okay, now X can be chlorine or bromine. Okay. All right. The third reaction, if you recall, is sulfonation, where you treat it with fuming sulfuric acid, which is sulfuric acid mixed with sulfur trioxide. That can be converted to a sulfonated benzene, SO3H. Now here is where we had studied the sulfonated benzene can be taken back to the benzene molecule by treating with dilute H2SO4. Okay, so see, I have put the arrow in the opposite direction here, saying that if you treat this sulfonated benzene with dilute sulfuric acid, you can bring it back to the benzene original molecule. Right? Okay, the next reaction we have studied is Friedel-Crafts alkylation. Friedel-Crafts alkylation. Oh, let's write the reagents there. Okay. So Friedel-Crafts alkylation is when you take a like an RCl, alkyl halide, and treat it again with the Lewis acid. Then you can place a R group on the benzene ring. Okay, that is Friedel-Crafts alkylation. And then Friedel-Crafts acylation was where you take a acyl group, right, RCOCl, and again in presence of aluminum chloride, where you can substitute the hydrogen with the acyl group. Okay, here is where we studied a further reaction that if you can actually do reduction, Clemenson's reduction, in presence of zinc, amalgam, and HCl acidic conditions, where you can convert this or reduce this ketone here, right, into a alkyl group. So we have 2 carbon atoms, so we have 2 carbon atoms here. Okay, so this is a reaction which you can also remember for synthesis steps. Here again, one more reaction we had studied earlier, that if you take NO2 and then react it with zinc in acidic condition, you can convert that NO2 group into a NH2 group. Okay, so we haven't studied direct method of benzene to an NH2. However, you can go this pathway where you convert benzene to nitrobenzene and then treat it with the metal zinc or iron. Okay, so you can use zinc or Fe, but in acidic condition HCl, where it converts to NH2. Okay, so some of these mechanisms I'm not expecting you to know, like one is this, one is this. However, the rest of it you should know. Okay, so you need to look at the mechanisms of Friedel-Crafts alkylation, acylation, nitration, halogenation, and sulfonation. Sulfonation is the only reaction that is reversible, where you can change the concentration of the sulfuric acid and get the desired product. Okay. All right, now coming back to our problem here, we have a target compound which is 3-bromoaniline. Okay, right? 3-bromoaniline. So what will we do? What would be our first step here? Should we put the Br or should we put the NO2? We do not know how to put NH2 yet, but we can put NO2 and then convert it to NH2, right? All right. So if you think Br is a ortho para directive, okay, it's an ortho para directive. So that means if you put Br first, then you cannot put any group meta to it, okay? But because see, these two groups are meta with respect to each other. They are at meta with respect to each other. So if you put Br first, you will not get any meta substitution because Br is a ortho para directive. So it is wise for us to do the nitration first. Okay, so we will start with take the benzene and nitrate it first. Here, when we are doing synthesis reaction, you do not have to show the mechanism. You just write down the reagents and the intermediate compounds. Okay, so nitrating mixture. This is the nitrating mixture. This will place the NO2 group on the benzene ring. So we place the NO2 group on the benzene ring. And now the next step would be to brominate it because NO2 is now our ortho para directive. Okay, so NO2 is I'm sorry, ortho and meta is NO2 is a meta directive. Okay, so that's why we will be able to use the next step of bromination, Br2. Now remember to always use Lewis acids for these reactions. Okay, AlBr3, and then what do you get? Br being placed in the meta position with respect to NO2. Okay, so see, now we have placed the Br correctly. But are we targeting this compound? No, we want an NH2, right? So our final step would be where you take this molecule and then use this reaction over here. That is either with zinc or Fe in presence of HCl, which will reduce the NO2 to an NH2. Okay, so see, now we have created our target compound. This is an example of a synthesis reaction. Okay. Another reaction would be, let's take another example, but I would like to erase this and do it over here. Okay, so that we can keep on using our this summary chart that we have drawn. Okay, we will need that at least till you know what reagents to use. Okay, so it will be a good practice to have that handy while you're studying. You may not be allowed to take, you are not allowed to take this reaction to the testing area, but you can, when you're practicing your problems at home or doing homework problems, then you can use this to understand the reactions. Okay, all right. Next one is, again, this question is the same. Starting with benzene, how will you convert it into the following compounds? Now I have a different structure, which I put here. So what I have is a PR. So actually I have an example where I have the 3 substituents. Okay, a long alkyl chain, NO2, a PR. Okay, this is what I need. So benzene, the question is take benzene and convert it into this one. So this is my target compound. So what are the groups? We have an NO2, a PR, and an alkyl chain of 1, 2, 3, 4, 5, a pentyl group. Okay? Now, if you look at each of these groups that are attached to benzene, PR is a ortho para directive. Alkyl groups, these are also ortho para, and NO2 is a meta directive. Okay? So if you want to place a group like Br or alkyl group, you can put that, but then the next incoming group will either go ortho or para to them. If you put NO2 first in there, then it will direct the incoming group to the meta position, and you can see that there is nothing meta to the NO2 group. Okay, so that's why our first step should be somewhere where the ortho and para groups have been placed first. Okay, so we'll take the benzene treat it with. Now in this case, you have to be very careful that you cannot use a alkyl halide, because remember, when you have long chain alkyl groups, then rearrangements can happen, right? So the best method would be to use a acyl chloride with total of 5 carbon atoms, right? Because we need 1, 2, 3, 4, 5. So I will use 1, 2, 3, 4, 5. I have an acyl chloride here. Okay. Don't forget the Lewis acid, AlCl3. This will place my acyl group on the benzene ring. 1, 2, 3, 4, and 5. Okay, so including the carbon of the ketone, we have 5 carbon atoms. 1, 2, 3, 4, 5. Okay. All right. So now we placed this, but this is actually a meta director. Okay, if you go back to the ortho-para directing charts, you can see that a RCO group is a meta director, which is actually good for us, because see, with respect to this, Br is meta. So now, since we have a acyl group here, which is a meta director, the next step we can do is bromination, because then we can place the bromine correctly at the meta position with respect to the acyl group. Okay, so we have the intermediate product where Br is here now, and our acyl group is also here. Okay, all right. Now, what should be my next step? Because I have to yet to place the NO2, right? So if I take HNO3 and H2SO4, which is what is needed for NO2, then it can either go ortho or para with respect to Br, right? So in order for the next reaction to happen, we can maybe reduce this first. Okay, we can reduce this first by using the Clemenson's reaction, where zinc, mercury, and HCl. Okay, so you reduce that. This first, yeah, that will convert this into an alkyl, because that is what we want, right? Now this is an orthopara. This is an orthopara. Okay, we have 2 orthopara groups here, and if now you treat this with HNO3, H2SO4, okay, because that's what we need for putting a NO2 group, we can convert the molecule to this the final product. Okay, so where your NO2 is placed here, because that is ortho with respect to the pentyl group. Also, it is para with respect to the Br. So both of them are giving us reinforcing effects, right? Because see, this we have ortho-para. This is also ortho-para. So when you place the NO2, it is ortho with respect to the alkyl group and para with respect to the NO2 Br group, right? So we have a reinforcing effects, right? So both of them are helping the NO2 group go to this position, and that's how we get our target product. Okay. Let's do one more example. Where benzene has to be converted to okay, this is my product, final product. So the first step would be, so we identify what type of groups do we have. We have a orthopara. Okay, so this is orthopara. This is also an orthopara. This is a meta. Okay. Again, remember, we do not know how to directly put an NH2 group, so we will go through the pathway to convert benzene to NO2 and then to NH2. Okay. All right. So what should be my first step here? I can take the benzene and treat it with bromine, right? I treat it with bromine in presence of a Lewis acid. I can actually place the bromine onto the benzene. Alright, once it is done that, I can do the sulfuric acid, fuming sulfuric acid, H2SO4, and that can be placed, since Br is an orthopara director, the SO3H will be at the para position with respect to Br. There could be some product which is ortho with respect to Br. However, due to sterics, SO3H prefers to go to the para. Okay. Now, finally, to the HNO3H2SO4, where SO3H and Br, they're going to have that reinforcing effect, because see, this wants the new group to go to the meta. This wants the new group to go to the ortho and para, because it's an ortho para, but para is already occupied. So the only position that is vacant is this ortho position, right? So that this reinforcing effect will help the incoming NO2 group to be placed at this position. Okay. But this is not my target compound, right? I need to do one more step where I reduce the NO2 in presence of zinc, HCl, right? And we can reduce the NO2 group to the NH2 group. Now we have the SO3H correctly placed. We have NH2 and then place. So I hope this video is helpful for you to understand synthesis problems. I will also, in the next video, do some more practice problems for the exam. Until then, you use all these videos that have been posted to prepare for your exam.